Welcome to Lesson 8C, Induced Drag, Kinetic Energy. In this lesson, we'll analyze induced drag based on kinetic energy and control volume analysis. Specifically, we'll generate an equation for induced drag based on wasted kinetic energy. Before I get into the analysis, we'll analyze induced drag three ways: by looking at kinetic energy, by looking at momentum, and by looking at downwash. We'll do the kinetic energy analysis in this lesson and the other two in the next lesson. First, qualitatively, recall the trailing vortices where you have air spinning around in these vortices behind the wing. These vortices have kinetic energy that's serving no useful purpose other than spinning up the air, so all of this kinetic energy is wasted. Where does this kinetic energy come from? The wing must produce this kinetic energy that is wasted. In other words, the wing must do work on the air to generate the wasted kinetic energy. This is the basic concept of our kinetic energy argument. This work that the wing does is felt as an imbalance in the pressure distribution on the wing, leading to induced drag. In other words, the wing is pushing against the air, and the result is induced drag. Now let's consider this quantitatively. We'll consider steady level flight. We'll apply a fixed control volume relative to the stationary ground, in other words, not moving with the wing. We're assuming incompressible flow and irrotational flow, except in the center of the vortices, of course, which are singularities. We'll model a simple chopped wing, in other words, a two-dimensional wing that is chopped off on both ends so that it is finite span. Here's our fixed control volume and our chopped off wing with the trailing vortices. We'll let this position of the wing be at some time t, but consider a short time later, dt, where the wing has moved forward a little bit. In other words, at time t plus dt, the wing is now located here. It's moving at speed u. The distance that it moves in this time is thus u dt. So consider a little volume at the back end of this control volume, which I'll shade here, of thickness u dt. And the area of this face we'll just call area A. Now imagine little cylinders of that same length u dt around each of these trailing vortices. There's kinetic energy in these cylinders as the air is spinning around in the trailing vortices. Comparing time t to time t plus dt, since the wing has moved a distance u dt, this amount of kinetic energy in the trailing vortices represents additional kinetic energy at time t plus dt than what we had at time t equal t, because these trailing vortices are now longer by distance u dt. Let me be a little more consistent as I try to draw this dimension three-dimensionally. Since the trailing vortices have gotten longer in this time period, there's extra wasted kinetic energy within this shaded volume. Another way to think about it is that all this kinetic energy in this little segment of the trailing vortices is newly generated by the wing moving this little distance in time dt, and all of this kinetic energy is wasted. It's doing no useful work. We can argue that the total kinetic energy at time t plus dt is larger than it was at time t, since the trailing vortices are longer. The kinetic energy is increased by the amount of kinetic energy in this shaded volume. That's how much energy is wasted in time interval dt. With this in mind, we can do a simple energy balance in the control volume. First of all, let di be the induced drag force. In our notation, we can write di times u dt equal the integral over vs, where vs is the shaded volume in our diagram, and we integrate the kinetic energy 1/2 rho v squared dv, where remember that v with the line in it is a volume and v without the line is a speed. This term is the kinetic energy per unit volume, and when we integrate over volume, we get dimensions of energy. Here we have a force times a distance, which also has dimensions of energy or work. So this equation is balanced dimensionally. But from our diagram, Vs is simply the thickness, u dt, times the area of the face, A. And the magnitude of the velocity squared, at any location within our shaded volume is the sum of the three components u squared plus v squared plus w squared, but we'll neglect the velocity component in the x direction. Let's examine the terms in this equation. The term on the left is the work done by the wing to overcome induced drag in time interval dt. And on the right side, this is equal to the total amount of additional kinetic energy of the air in the control volume, again in time interval dt. As we already stated qualitatively, through induced drag, the wing is doing work on the air, generating kinetic energy of the air, which is wasted. And it's the induced drag that generates this wasted kinetic energy. So setting v squared to little v squared plus w squared, and knowing that dv is a times u dt, this equation becomes diu dt equal 1/2 rho. Since we have incompressible flow, we can take rho outside the integral, and we'll split the volume integral into the integral over area A of v squared plus w squared dA times u dt. In other words, if I resketch the shaded part of the control volume, A is the area, and we have these two little segments of the trailing vortices with kinetic energy of the air inside this little shaded control volume. And so to do a volume integral, we have to integrate this kinetic energy per unit volume over the area, and we're approximating these little segments as horizontal so that we just take this area and multiply by the thickness, which is u dt. We'll notice that u dt appears on both sides of the equation, so it cancels out. Thus we have an equation for induced drag, di equal 1/2 rho, integral over the face area, v squared plus w squared dA, at the downstream plane of our control volume. Thus, in a few simple steps, we've generated an equation for the induced drag. I comment here that in order to get all the kinetic energy, area A can extend to infinity, and you'd have to integrate this term for all the v and w components of velocity in area A. In practice, since the speed dies out with radius, you don't have to go to infinity. So we conclude induced drag is directly proportional to the wasted kinetic energy of the trailing vortices. This is what we said qualitatively as well. Does it matter how far downstream you take your slice for area A? Yeah, we was thinking that the further you go, the weaker them vortices. Don't them vortices dissipate by viscosity? I wish you would dissipate. I wish you would disappear. Whoa, guys, be nice. In real life, the trailing vortices do dissipate, but we're approximating this flow as irrotational. The vortices don't dissipate. So it don't matter at all how far downstream we go then. That's right, Dick. I'm Duck, not Dick. Don't insult me. Sorry, Duck, but even if we account for viscous dissipation, it won't change our results. Viscous dissipation just heats up the air. It converts kinetic energy into internal energy, so the total energy does not change. You'd have to add an internal energy term in here, since some of the kinetic energy is converted into internal energy or heat through viscous dissipation, but that would not change our final result. You'd get the same answer for the induced drag, regardless of how far downstream we do the analysis on area A. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.